Wednesday, and she asked me to record, so I'm going to do that. But let me jump into the, I guess we'll roll with the PowerPoint presentation at this point. The title of today's lecture is Probability and Confidence Intervals. And when you're looking at probability, the probability of an event happening is usually recorded as 0 or 1 or some number in between. If an event has a probability of 0, that means it will never happen. If the event has a probability of 1, it is certain that it will occur. What are some examples of a probability of 0?
Sorry, I'm on some campus, there's something about like lesson 12 lecture notes that we have to turn in. Are we doing that today in class? Is that something we have to do afterwards?
Oh, it's not assigned, just if you go to the lecture 12 lesson notes, you can download the PowerPoint if you wanted to follow along on your own. You don't have to. There's no assignment that's due with today's lecture.
Oh, okay. Sweet.
What's an example of something having a probability of 0?
A male having a child.
A male having a child, that is,
There we go. Yeah.
that is an example. What about the probability of 1?
A woman having a child.
You need oxygen. Yeah. The way our biological system is set up, we need oxygen to survive, so we need to breathe. What about a low probability?
Being warm in Rexburg during the winter,
So it's possible,
but it's a low problem.
it's low probability.
Yellowstone exploding in the next couple of years.
Yeah, hopefully that's a very
It's
low
2020,
probability.
Have you been watching it?
You probably haven't, honestly.
That's the thing, is that the people have been saying in documentaries for years that it's going to erupt within the next like year or two, and I've read stuff like that in like 2013. So
Yeah, I'm not.
I mean, it was a surprise last time.
I just wouldn't throw it out into the universe, not until this year's over, like, just wait.
Yeah, let's not proclaim it. I'm scared for 2021.
Cool, good depth.
What about the median probability?
Everyone did that.
What's the
Everyone who
median,
did
an
that
example
COVID
of median
dies.
probability?
It hits us later.
getting in a car crash with the roads so bad,
I would say it's a high probability.
like not even like getting like hurt, just like crashing your car in some way, shape, or form.
Well, that's-
Oh, yeah.
I would say that's actually a fairly low probability.
I've crashed my car every winter for the last
Every winter,
3 years.
so how many times have you driven?
Well, not like in a bad way, is that like I'll run into like a snowbank or something, because like in my hometown, the roads get so bad that you just like can't drive in winter. Like it's something you should not do.
Are we talking about low or high right now?
Medium.
Oh, medium, okay.
So Josh and then Megan.
So would a median be like a 50-50, like flipping a coin?
Yeah, or 60-40, somewhere in there.
Okay.
Okay.
I was gonna say something like getting hurt while playing a sport.
Getting hurt, yeah, because I think it happened. We get hurt.
Everyone on a team gets hurt.
There's different levels of how much you get hurt, but you know, if you haven't exercised in a long time, you're gonna be sore. That is, I mean, you could consider that being hurt too.
Okay, sort of a high
That's a high probability.
probability.
If you play hockey, that might be a high probability. The first week I played hockey here, somebody hit me in the neck with their hockey blade on their stick, and I had a big bruise for a couple of weeks.
I don't think I ever looked at hockey games now.
That's funny.
Most of the time I played it, I don't get injured, but the things do happen. But one time I was driving somewhere, this is when I was going to school in Provo. I was on a double date, and I didn't really know I knew one person, other person in the car, and it was raining really hard, and it was hard to see, and I kind of jokingly said, like, wow, these aren't very good driving conditions, but you know what, it's been 2 weeks since my last accident.
Yeah.
I was just joking though, I normally don't get in accidents. As my wife and I brainstormed a bunch of ways that how probability it can be used. The first one I thought of was speed limit. And then I found a journal article that talked about speed limits. And there have been limits almost as long as there have been motorized vehicles. And one of the main reasons why we have speed limits is because it's to reduce the probability of an accident. If you drive by Smith Park, not far from here, The speed, I think that direction, if I know mine, anyway, it's, the speed limit is about 20 miles an hour around the park. Why is it so low?
Because since it's a park, there's a higher probability of children and families being in the area.
Yeah, there's a lot of people running around, especially during the summer. I haven't seen it as much during the winter, but during the summer, whenever I drive by there, there's lots of families, or lots of groups of people doing all sorts of activities.
I'm always at the park in the winter.
Weather forecasting, there's a lot of jokes about how that can be the job where you're wrong every time and you still get paid. But the weather forecasters, they do have some information that they use, and they are useful. I think the best weather forecasters might be if you can find an old farmer who has been in an area for a long time. Usually he or she is really good at predicting what the weather is going to be like. If you live in a coastal community, you can talk to a commercial fisherman and the same thing, but they rely on the weather for their livelihood. But there are a lot of, if you understand about how the topography affects weather, different weather systems, you can come up with pretty good predictions that can change what type of activities you're going to do. With sports, whether or not a team is going to win, there's a lot of efforts put into looking at both probabilities. The same thing with politics. When a politician comes out with a new policy, he or she might hire a bunch of economists to figure out what might be the likely outcome. And they're using probability in there too. How many of you have bought car insurance before? Your insurance agent dealt with probability. Who pays the most for car insurance?
People with boys.
Yeah, whoever buys a policy where there's a teenage boy driving. Why is that?
Because there's a higher probability of them getting an accident.
Yeah, there's much higher likelihood that they'll make a claim. A claim will be made
Oh, yeah.
because of that. When we bought our house in Rigby a few months ago, I was talking to our insurance agent and they quoted us the price and I thought that's weird because what they were quoting was higher than what we were paying in Juneau. And in Juneau, houses cost a lot more. And if you hire a contractor, you pay about twice as much as what you do in this area because of the different labor market. And we asked her, why is it so high? And she said, well, the last several years, there have been a bunch of hailstorms and a lot of homeowners have made claims to get their roof fixed. And when you buy an insurance policy, you're hedging your bets, but they are against you too. They set the price based off the likelihood that you will make a claim. And that's how, what that determines what you pay. With lottery tickets, and I've heard that the lottery is a tax against people who don't understand math. When I lived in Provo, I'd go down to California to visit my sister a bunch and drive through Vegas. And I thought it was interesting, driving by these big casinos, they'll have signs that'll say like, we pay out 97%. I mean, what that means is on average for every dollar you pay, you get 97 cents back. And some casinos, they'll even broadcast what their payout is. When we play games, there's a lot of probability. This last weekend, has anybody played the Farmer's Game? It was made by a farmer, that's how it's advertised. So you grow these crops and then you try not to go bust. But I mean, there's a lot of board games that we play where that take into account probability. With college, there's when you put in when you apply to go to a college or university, the admissions will look at your application and they'll determine the likelihood that you'll be able to graduate, and that gets used as to whether or not you get accepted to the institution. How many of you use probability when you're planning your classes? When you look at what's the likelihood you'll get a good grade, depending on what section you'll get from a class you want to take, or how well you expect to do in that class. I read an interesting journal article a couple decades ago about, there's an economist who looked at grade inflation, and what I thought was interesting about that is, what he said is that in the 1960s and 70s, in some of the majors such as English and history and the arts, they experienced some grade inflation, but in engineering and math and biology, there wasn't grade inflation. And as a result, more of the marginal students ended up changing their majors, and there's less students in college who graduate in the hard science fields as a result of that. I mean, if you're looking at how well, if you're trying to decide what to major in and you get a C in your biology class and you get an A in your history class, which one are you more likely to be majoring in? And that doesn't mean that you did worse in one or the other.
Oh, kind of.
Kind of not, well,
I mean,
inflation.
A and C.
Yeah. But if you look at what the average GPA is for everybody that major, for among different majors, that might inform you a little, that maybe you're not doing as bad as you thought.
Yeah.
How many of you have hired people before? Yeah, or how many of you have been in a job interview? Almost all of us. A lot of the hiring process is to determine who will be most likely to be successful. It doesn't mean that exactly will happen, but a good set of interview questions will help the hiring team have information about the likelihood, the probability of somebody being a successful employee in that position. And also with marriage, I mean, you take a big risk when you choose who your spouse is, and there's a lot of, there is a bunch of uncertainty involved there too. And that doesn't mean, like I look at my parents' lives, my dad was raised by a single mom. On my mom's side, her parents divorced when she was young. My dad died just a few years ago, but they were like the model couple. They were different in a lot of ways, but they complemented each other. And what they told me a lot of times that they based their marriage on the gospel. It requires a lot of forgiveness, a lot of effort, but there's ways that you can increase your chances of success. When I was younger, an old Inuit elder told me, like he said, when you go hunting, if you ever catch anything, it's because you're lucky. And that's the only reason. And he said, now let's talk about ways how you can increase your luck. And then he talked about having good moral character, respecting what you're hunting. And then he also talked about some hunting techniques. But I thought that was an interesting way of looking at things. You're only lucky, but you can increase your luck. In our reading, we had a few vocabulary terms. Well, I'll just read it out. The probability, we talked about that, is probability of 0 means it's not going to happen. Probability of 1 means it certainly will happen. Most of the time, something happens in between 1 and 0. The sample space of an event is a list of all the possible outcomes that could happen in the event. And if you come up with a probability model, if you take the sample space and you measure what each of the probabilities are for those, that will give you a probability model. There's two types of probabilities. There's empirical and there's theoretical probabilities. Empirical is determined by looking at data, things that happened in the past, or you can recreate an event by doing things multiple times and computing how often the desired outcome occurs. A theoretical probability is when you take information that you already know, then you apply mathematical formulas to predict how often the desired outcome will occur in the future. And a parameter is a number based on the survey of the entire population. That can be difficult to do. A parameter will take, it can be costly financially, but it can also be costly in terms of the amount of time that it takes for something like that to occur. A statistic is a number based on the survey of just a sample of the population. So you pull out a subset and then you try to determine something based off of that, and you create what's called an estimate. So statistics are used to estimate the true percentage or the parameter for the whole population. And one of the things we use for that is the margin of error. You compute the margin of error by taking 1 over the square root of n. And if you look on this graph that I made, on the x-axis, that's the sample size. On the y-axis is the margin of error. So as x continues to increase, and then then you get a smaller margin of error. And then are there any questions about any of those terms that we talked about?
So you square root n. Not in the reading that. Maybe I'm just never mind. Just forget what it is.
if we weren't in a pandemic right now, we could do this in-class exercise, but well, we have 3 models to choose from.
We could do it, but.
And the way I created something similar to this, let me pull it up. So in the absence of being able to do this in-class exercise, I created this, and actually this one has a little bit of a larger population size than what we have in class. And so the way this works is you can download this from Canvas. It's called, I think it's called Pandemic. And this one has 2,000 people, but I think you can build it up to almost 100,000 people. And it takes a while to compute depending on how fast or slow your computer is. And the way this works is it starts off is seeded with, so 0 means you're not infected, 1 means that person is infected. So at the very beginning, among all 2,000 people, person number 3 is infected. We could make it different. And that will change the outcome. You can have person 2 or any other person or different number of people that are infected. And the way this works is each one of these people has a random interaction with somebody else. That's what this column D is. It randomly selects somebody from that whole list. And then and then they roll a die, that should be die, not dice. But they roll a die, and if they get a 6 and one person's infected, then the other person gets infected too. And it goes through this, there's 50 different interactions. You start off with 0. That's the first interaction. You have 1 person that's sick. The second interaction, you have 3 people that are sick, that are infected. After the third, it's not until the 5th interaction with 1 more person, and it continues on. And you can see how it changes until everybody is infected, according to this model. And I have a couple questions for a little bit of a discussion. What do these results tell you about the spread of disease?
Spreads fast.
It spreads fast? Well,
Well, I mean, not fast, but like once it starts.
it starts off slow, then it gets faster.
Based on the interactions.
Yeah.
It kind of reminds me of like exponents, because it's like with exponents, like 2 times 2, then it's like 2 times 2 times 2, and
Yeah.
then it would be 4 times 2. Like it starts small and then it just rapidly,
It grows at an accelerated rate.
yeah, exponents.
Yeah. How is probability involved in spreading this infection?
From my point of view, it kind of looks like, hold on. The probability is a lot higher as we go on, right? As people start spreading it. I was gonna say something like, it's almost like they're increasing the number of dice to roll, in theory.
Yeah, I mean, you can look at it that way because if you're not infected, you're not really going to spread anything.
Yeah.
And what happens early on, if you look at, let's see, we have the second person who's infected. The first interaction they had with somebody, the 2 was rolled, and so that person number 134 did not get infected. There's no transmission. And the probability is there because if you come in contact with somebody, who has a cold, there's no guarantee that you will get the cold. It depends on a number of factors, like for example, how easy that disease is to be able to be transmitted, the infectious rate, I think they call it. Did we use an empirical or a theoretical probability for this model?
Theoretical.
Theoretical, well, almost.
Okay, empirical.
Empirical.
Okay.
Give it a 50-50 chance. chance there.
So with the empirical, you look at data that actually happened, even if it means you create your own data. With theoretical, you're using a bunch of models, a bunch of math models instead of something like this. And so I mean, this is a empirical one because it's a simulation. If you build a simulation, that will always be an empirical. It's a pretend universe where things happen.
Okay, because I was gonna say theoretical, because imperial, from my understanding, was like past things. But this is all like hypothetical, whatever that word is.
Yeah, it's hypothetical, it is.
Yeah.
But we're creating a whole bunch, and if we were to run this again, and so I'll change this, actually, just by changing this, it will, takes a little while. It's computing everything. Well, the graph did move a little bit. If we were to look at these numbers, so now at the 5th interval, there's only 2. Oh, there it goes. Not caught up. So now it's the second interval that somebody else was infected. And this one happened to grow a little bit faster. There's still the same number of people who were infected starting out.
Wait, so is it imperial because it's building off of the past data?
It's creating a data set that can change any given time. If you build a theoretical model, I mean, you might compute some confidence intervals, an upper or lower bound, but the theoretical model is not going to be changing. An empirical model will change every time you run it. Or every time you collect the data, it might be different. It might be pretty close. And that's what happens in the real world. There's often, we live in an empirical world.
So, just to help me wrap my head around this, it's a little confusing because it's theoretical data that can change what we're calling it empirical. So like, for example, would a trend line equation, like we're finding what possible future data could be, would that be empirical? Or would that be, so that would be empirical data, even though technically, well, actually that would be changing. Okay, so it just depends on if the input is changing or not, whether it's empirical or theoretical?
That might be a good way to look at it.
Okay.
If the data points could change every single time you run the model, and then it's an empirical probability.
So like, for my trend line equation assignment thing, I did like numbers of missionaries in the field, so it's empirical because the missionaries change every year, but if we had the exact same amount of missionaries going out every single year, it'd be theoretical?
No, it'd be empirical, because if you were to run the experiment over again, you might have a slightly different outcome each time.
Okay,
So a theoretical model involves writing a whole bunch of formulas.
okay,
An empirical model involves looking at a bunch of data that gets collected. It's either collected on real world stuff or things that get made up, but it is collected data for empirical.
okay, so empirical data, because I've done stuff with empirical data before, but that's collected data, but we can find what we think is future data with empirical data, and it's still empirical?
Yeah,
Okay, that's just where it's a little like shaky, because it seems like if you're getting like a possibility of future data, it should be theoretical, because technically it hasn't happened yet.
Yeah.
I guess in that sense, I mean, yeah, you could use the word theory in that definition.
Kind of like with a trend line, we'll sometimes do the years, like the input is what year it is, and then kind of estimates like stuff based on data that we already have. So say that we do an input of 2021 for something that we don't know yet, would that be theoretical or empirical?
That's based off of empirical data.
Okay, so it's based off of empirical, therefore it is empirical?
Yeah.
Okay.
What's an example of a theoretical one then?
An example of the theoretical, let's say, what's the likelihood that you'll get 3 heads in a row? I mean, you could roll a dice a million times.
Or is it because
flip a
like you
coin.
know exactly what the outcome could be?
Yeah,
Like you already have the end conclusion, it's just which one of those? Because with empirical,
So-
like you're taking the data and you're making new data out of that, but then with theoretical, there's already the data and then you're just.
So theoretical is like we there's no way we could possibly know in advance what it could be. It kind of is just up to,
Empirical means you're using a data set.
okay,
Theoretical means you're building a model. Like, for example, if you were to roll 3 heads in a row, the probability is 1/8. That's a theoretical model. If I were to flip a coin 3 times, 1,000,000 times, I would get some number really close to that. That's another way that I can figure out.
Is it kind of like, okay, I'm not trying to throw a curve in this empirical and theoretical, okay, but
oh no, go ahead.
is empirical kind of like, well, theoretical is kind of almost like physical, like it's like physically, like you could not physically figure it out in a way, because like, for example, heads and tails, you can flip a coin and do it. Empirical is just you make a data set and find a probability even though you don't have physical evidence. Kind of.
Yeah, so like the theoretical model, you develop in an ivory tower,
Yeah.
and then an empirical one, you're in the trenches collecting data.
Empirical is based off of a statistic that we know to be true.
Yeah, off of a bunch of data, off the data set.
I think that makes sense.
Okay, and then in your Mobius homework, they'll ask you that question a whole bunch of times.
Okay.
That should
Throw it in there.
I'm really preparing myself.
When you're doing the Mobius homework, please use a how did I do. That'll increase your
That's
likelihood.
my favorite tool because I'm like.
Yeah, I just hate that it's not
okay,
on
is
the
this one?
review.
No. Okay, is it this one?
I wish it was
No,
on
I'm just kidding.
Even if I can get it right, I'll go in and I'll be like, how did you do?
It's like,
Every single question, I'm like,
I know, there's
Oh my
questions I know I got right.
but you just
I just
gotta
have to hit that button.
you just gotta make sure, you know?
Then looking at this graph, how does this graph help you understand the spread of disease?
Every person counts.
Wash your hands.
Well,
Dang it.
here's the next question that pertains to that. What steps can be undertaken to help slow the spread of this disease?
Less interaction.
Less interaction?
It's like they've been telling us that the whole time.
And if you do that, or like wearing a mask, all those things, what they do, so you have in what is it, column G, when you roll a dice, when you reduce the probability of the transmission, that's what the masks are supposed to do, or the social distancing. Because then that reduces the likelihood that that next person will receive that infection. Well, looking at diseases is kind of negative. What are positive things how we can apply this out of the model to?
Say it one more time.
Instead of something negative, like a disease transmission, what's a positive example that we can apply this to? Let's go to Joshua again for sure.
Well, here's an example. So you can, a smile, for example. Like you can smile at somebody, they might be having a bad day, and then they can smile at another person, and it just spreads like that. It could happen. I don't know what the probability is,
It's
but.
hard to track.
You could kind of apply that to like the world. Like how many good things happen with like the world from little things
Yeah.
you do every day.
I was gonna say the stocks.
Technically, that could be a bad thing.
So you put your investment into like, I don't know, you can put it into Tesla or.
Oh my goodness.
You could put it into marijuana, I'm not saying do, but you know, it would go up, but Tesla, I would say do Tesla, just, they're two totally opposites, but stocks wise, they could just shoot up, and I should have done Tesla like, when it first came out.
Yeah. One example I thought about it, just over a week ago, President Nelson asked us to put positive stuff on our social media. What have been some of your experiences with that? Have you seen a change? Have you felt a change because of that?
Majority of my feed for the whole week was good thanks.
That's all it was from my feed, I literally was like, oh my gosh, I love it, but I can't stand it, but I love it.
One thing that was kind of cool is, so I'm from North Dakota, so most of the people I follow aren't LDS. And I actually had friends from school that were like using the hashtag and they didn't know like that like everybody that was LDS was using it, but they started using it, which is kind of funny and cool.
Yeah, people do that too.
Yeah.
So we see that upward where it's infectious, it spreads. It's a good thing.
Happy is an infection.
Christian,
I was wondering, I know it's a little late, I was wondering if you could show by chance an example of the 95% confidence interval, like
Yeah.
that one on the quiz, I was like really thrown off, because that one did not make sense to me.
is that the one with the election?
I can't.
What was that?
The coin toss one?
What was the question?
Like the second to last one.
It had something to do with an election.
Is that the election one or was it a different one?
I couldn't recall,
The electionist, it was like Andrew had 51% of the votes, and then some other dude had 49. And then there's a 3% margin of error. And then
oh,
we had to calculate what the 95% of.
The confidence, it's like a confidence
That thing.
percentage or something.
Yeah, the confidence
Where you
interval.
have to like
Yeah, confidence
add it
interval.
subjective.
Yeah, so if you have 51 plus or minus 3, what is 51 minus 3? 48, right? And
okay, yeah.
54, and 49 plus or minus 3.
What does that have to do with 95% though?
That's a good question. You're 95% means you're pretty sure that's what's going to happen. And
But they're giving themselves like a 5% of like 51% said this, but they're giving them like a 5% of like, that might not be true.
Yeah, and so I mean, I think when you say plus or minus 3%, you're 95% sure that's what the value is.
Okay. So I have a question. If we have to find like the 80% confidence, how would we do that? Or
80%.
does that not, is that not gonna happen?
So to calculate the error term, it's 1 over the square root of the sample size.
Okay, cool. Just make sure. Cool.
1 over the square root of n, whatever that sample size is. Let's look at that slide.
But isn't that just for like the margin of error?
Yeah,
So it's the same thing. Okay, cool.
yeah. And so if you're looking at with this person, I mean, it's a pretty close election, 51, 49% in the sample size, plus or minus 3, that means anywhere from 48 to 54 for that person, 46 to 52. There's a bunch of overlap, which means it really could go either way. You can't really call that before the election. Was that your question, Christian?
Yes, that was, I answered one, there's another one on the quiz that was different, it was different, I remember it had like, what's the 95% chance, and it showed like A, B, C, and D, and then I would have to find it, but we can't access the quizzes, unless we can now, but I'll look into it, so.
Okay. Thank you. Shoot me an email. Be happy to answer your question.
Okay.
Did it give you like the sample size and then how many people voted for that? And then like, was it like the city one?
I couldn't recall. Maybe it was the confidence interval.
Like where you had to like find it.
It was like the unemployment in each city. Was it that one?
I couldn't recall.
She's got the quiz pulled up right here. So we got, that's yes.
Oh my gosh, are we doing the Studio C video? That's amazing.
I'll bring
love
the computer
that.
back here. Don't judge me.
That is one of my favorite videos, like ever.
She just took your quiz.
I don't think we'll have time to watch that, but there's a couple of videos you can find it off the PowerPoint as links if you wanted to watch the movie. The Studio C, there's a brother and a sister. And the sister gets really bored and she wants to flip a coin a bunch of times.
I
And she
remember
keeps-
that one.
And she keeps calling it every time.
Yeah.
And then the other one from a movie called Rosencrantz and Guildenstern are dead. At the beginning of the movie, and one guy keeps flipping a coin, I think he gets heads 78
I thought
times. That's funny.
That's empirical.
Did you find the,
Yes, the problem.
Yeah, it's like,
It's-
I think everybody like didn't get that.
Yeah, it's question 6.
Slowly.
It's, you asked a sample of individuals what kind of animal is their favorite.
Yes.
Of the 167 individuals in your sample, 52 of them answered dog. Which of the following gives a 95% confidence interval for the true percentage of individuals whose favorite animal is a dog?
Wait, can I like guess on how to do it?
Yeah.
Okay, so you do 52 divided by 167, and then you take that and then you put it into, because then that's like your like portion, right? And then you take that and you find out the margin of error by doing the 1 over square. Yeah, and you put the n is the answer to that, the 52 over.
Yeah.
Or,
So
Yeah.
for 0.311.
Oh, so you do 52.
Wait, is, you put 167, you're saying it's the
Answer from the
answer
division.
from that. So is it the answer from that or is it 167?
so the 167 is the n, so
oh,
1 over the square root of 167. So what is that?
What's the
7%?
52 divided by 1? That's the 0.311.
so that's like
So 31,
31%, right?
yeah, 31% likes dogs.
And then you find out the margin of error by doing that
Yeah.
with the total number.
Is that about 7?
Yes, yeah, it's like 7.
Okay, let's call it 7%. Plus or minus, whatever.
Yeah.
So you have 31.1% plus or minus 7%. So you have, what's 31 minus 7? 24% to
38.
38.
And then that's the 95%
Yeah,
confidence.
does that make sense? Well, okay, the percent of people that like dogs, there are 52 out of 167. So that's how you get 31%. Does that make sense?
Oh,
Yeah.
okay,
Yeah.
okay, and then you put, okay, oh.
And then it's just like the range, like the
Like
plus
all-
7 or 9.
Yeah,
Okay.
and you get the 7% by taking the whole sample size, 167, and 1 over the square root of that. Yeah. I did it right, but yes. I'm just kidding. Yeah, that's how you do it.
Thank you.
Nice.
Good humor.
If you were to, how many of you like to play Settlers of Catan?
I never played
I played it twice.
You never played it?
I lost twice.
I like playing it.
One of my, so my wife, well, before we were married, she bought a game for my birthday, and I pulled it out, and one of my roommates was there, and he said, oh, I like that game. So we invited him to play with us, and like in 4 moves, he won. Okay? But he served his mission in Germany, he had like a German Settlers of Catan. Anyways, he was really good, he knew how to work the probabilities. But when you roll the dice, then there's different outcomes. Well, there's little tiles with circles on them that are put on the board. And the more circles there are, the higher the probability of that roll. If this graph, this chart here, shows the probability of each one of these rolls happening. So the number 7 has the highest probability, and then 6 and 8 are the next lowest, and so on. Actually, no, that chart shows with a count of how many there are. So if you want to find out the probability of rolling a 7, you count out all the 7s and divide it by the whole chart. So there's 1, 2, 3, 4, 5, there's 6 sevens in here, and there's 36 chances that might happen. And so you take 7 divided by 36, and that will give you the likelihood of the 7 being rolled. And what's the probability of rolling a sum of 5 or less? And you can use a number from this chart.
chance.
29%?
Yeah. Sorry.
I got 27.
I got, or 28, sorry, 28%.
Yeah.
28%?
Yeah.
Isn't it 27.8%?
27.8.
Yeah.
Okay.
That was a healthy round.
And so you can compute this, so you have 1%, 2, or the possibility of getting a 2, 3, 4, I can't count. The probability of getting a 2, 3, 4, or 5, then you add those two. You add those together, you get 27.8%. What's the probability of getting a 6 or more?
Oh, 6 or more.
72.2.
How'd you come up with that? So
Yeah, I was like, what the heck?
So I did 100 minus 27.8.
yeah, because that's everything else here.
Oh,
Good job. And I drew this on here. Hopefully that helps illustrate why Josh was able to get that so quickly.
yeah. Because
You
I
know-
was like, it's not.
Quick fingers, man.
I was like, oh my
Just
God.
did it in his head really fast.
I just was at work all day. That's my excuse.
But if you get like an exactly 5, what's that likelihood?
Were you talking to me?
Yeah.
He is now.
Maybe 5?
Yeah. What's the probability of rolling a 5?
0.11.
0.11.
11.1%, right?
It's 11. I'm reading it.
And we could go through similar exercises for 9 or more, or 5 or more, that we did before. If you go to Canvas, I uploaded a couple of Excel files. One was a pandemic one. The other is an Excel file called, I think it's called something like,
Coin and dice.
yeah, coin and dice toss. And I did find a mistake in there that I uploaded, but it's not that big of a deal. It won't affect, there's a bunch of macros in there. And the first tab is called a coin toss. And there's those yellow buttons where you click on them and it simulates flipping a coin. And if you flip the coin once, you can flip a coin 10 times or 1,000 times. If you were to flip a coin 20 times, when I did this experiment, there were 7 heads and 13 tails. Does that mean that next time I flip, it most likely will be a tail?
I guess it depends on what data you're going off of.
Well, after 20 times, I had 13 tails compared to 7 heads. So shouldn't I bet on the tails next time?
I mean, you would think so, but
Maybe we just need more data. So if you flip it a bunch of more times, 100 times, you get 43 heads, 57 tails. So instead of a 35-65 split, you get a 43% versus, what is that, 57%. And that's why the error terms are important. If you notice the blue error terms are the upper bounds, the red are the lower bounds. intersect, I mean, really, next time you flip, you do have a 50% chance of it being a heads or a tails. If you were to flip a coin 1,000 times, you might get this scenario, 486 heads, 514 tails. That's a lot closer to 50%. And the more times, if you were to flip it a coin 1,000,000 times, you would have really close to 50%. And you can look at, if you were to roll a single die 60 times, this is what I came out with. The yellow bar shows the theoretical probability. I mean, you have a 16.7% chance of rolling any number on a die. In having rolled it 60 times, there were, it looks like 5 was one that was rolled 14 times. That's almost a quarter of the times it was a 5. But that doesn't mean, well, if you were to roll it 1,000 times, it evens out a little bit more. And then here's what happens if you roll it 1,000,000 times. You have, it looks like,
Did someone actually take time to roll 1,000,000 times?
Yeah.
well, when I said there's a macro that does it for you, and then I adjusted the macro to roll it 1,000,000 times, and then I clicked on it, and then I put the computer away, and the next day I came back and it was done.
Nice, it just rolled all night.
It did. And so that's, I mean, even though, so this is an empirical data set. You'll see that, see what number is the highest. It looks like number 3. But I mean, that the difference from 1, 2, 4, 5, and 6 with 3 is very negligible. It's very small. All of them are about 16.6%. And you look at the bar graph on the bottom left, it's really flat. And I did the same thing with a pair of dice. That's what the other tab is. And you have, I mean, by rolling it only 100 times, it looks like 6 is the highest likelihood. But then you give it a few more rolls, 1,000 times, it started to look more like what it would look like in theory. So if you look at this bar graph on the right, you can see that some of them are a little bit higher, a little bit lower as to what the theoretical is. The intersection between the gray and the blue bar is where the percent. And so if it's above the yellow line, it's above the theoretical value. If it's below, that means you roll less. But then if you were to roll a pair of dice 1,000,000 times, you would get numbers that are really close to what the theoretical would be. Because what's 1 over the square root of 1,000,000? It's like 0.1%. It's a very small margin of error. It's a lot more correct. What are some thoughts that you had or things that you learned from this lesson, either the online lesson or what we talked about in class today?
I think this is really interesting.
It's interesting.
Yeah.
There's some ways to like predict like the probabilities.
Yeah, I think we
It's not all just to chance, there are some
Yeah.
calculations, there's some formulas that you can follow to figure out what it really is.
Yeah, you can use a lot of formulas, but I mean, I think we all use probability a lot. I mean, like, for example, this morning when I was driving to Rexburg, I saw a car turn on a blinker. And so I expected that car to turn, to change lanes, and it did. I mean, I adjusted my behavior, I slowed down a little bit. And it's good to always, I mean, when you're driving, if you always pay attention to things, because you can reduce the probability of a negative outcome. I mean, you would expect, like one time when I was driving between Utah and Idaho, the speed limit slowed down, and I expected all the other cars to slow down. But as I looked in my rearview mirror, I noticed the semi had closed the gap by a lot. It's like, I was driving a little Geo Metro, and so I swerved right into the outside, into the construction lane, and this big huge semi went barely right by. And I mean, you look at, I wasn't thinking, okay, if I don't change lanes, the probability of it hitting me is going to be about 97%. I wasn't thinking about those numbers, but I did think, okay, it'll probably hit me if I don't change lanes, then I think it would have. I mean, we use probability all the time, whether or not we're assigning quantitative numbers to it. So, but it's good to think about what these numbers are, because then we can better understand the probability of outcomes as we make decisions in life. But we do face a lot of uncertainty in many of the decisions that we make. And so that's why understanding probability theory can help us make better decisions. Okay, any questions or comments? Okay, that's what I have for the lecture. And I have,
Are we watching Studio C now?
well, you want to watch Studio C now?
Yes, I do.
We can do that. Before I turn that on, let me just say a couple of things. There is assignment 12A that's due tomorrow night. And then there's a 12B homework assignment. On Wednesday, we have more probability that we'll be talking about. And then on next, then we have lesson 13, there's a reading quiz. And then after next week, a week from Wednesday, there's the Unit 3 exam review. And then you'll have the Unit 3 exam. And if you do really well in that exam, you won't have to take the final.
I'm very excited about that.